So state diagrams are also used to describe dynamic behaviors. So they are closely related to these activity diagrams, but we'll see how they are different. So whereas activity diagrams, they focus on what's going on inside the system, a state diagram focuses on the interaction between the system and its environment. So a state diagram consists of, no surprise, it consists of states, and a state consists of a state name, a bunch of state variables, and a set of actions. So in the state name is just a label for the state. Then in the state variables we describe variables that characterize the state, and the state actions describe the actions that we can take while we are in that state to go to another state. So here's an example. So here is one state, and here is another, and here is a state transition that takes us from the first state to the second state. So state, state, state transition. And then we can look a little bit closer at the structure of this state transition. A state transition always consists of an event, a guard, and a set of methods. So an event is an event that is supposed to come from outside the model. So a signal you get from outside. So somebody gives you input, or somebody tells you something, or somebody pushes a button. Then the guard is a condition that must be true. So it guards the transition, and when the event happens, and when the guard is true, then you pick one of the methods to go to the next state. So here is a very simple example. So this is an example from a pilot in an airplane, and this is at the state when the airplane is at the start of the runway. So this is called a ready for takeoff. So all the passengers are seated with their seat belts fastened, and the engines are running, and the runway is clear. So we now are ready for takeoff. So we are waiting for an event, and the event is called permission from control tower. And once we get the permission from the control tower, so then we can do all our internal checks once again. And if those checks are okay, so if all our systems are safe, then we can take the action takeoff. Okay? So here you see a transition, an event, a guard, and a method. So the event is called get permission from control tower. Then the guard is that all our checks must be okay, because if the checks are not okay, we are not allowed to proceed. But if we get the signal from the control tower and the check is okay, then we can do the action takeoff. And after the action takeoff, we will find ourselves in the resulting state being airborne. So these actions, they are modeled as if they are instantaneous. Well, of course they're not, because between starting on the runway and taking off, there's actually a few minutes running on the runway. But in these models, we pretend as if they are instantaneous. So unlike an activity, which takes time in an activity diagram, a state transition is supposed to be instantaneous. You cannot interrupt it. So this is the prototypical example of a state diagram, which is what happens in a ticketing machine, say in a parking lot. So in a parking garage, there's a machine where you insert coins and you get your ticket. So I'm not going to go through this diagram now in detail, but by now you can read all these transitions. So at the beginning, the machine is not doing anything, so it's in idle state. And when a signal happens, namely somebody inserts a coin, right, then we go to the next state. And then after that next state, somebody has to select a ticket, and so on, right? So you can read this diagram and see that each of these transitions has a guard and an action. We can also have concurrency in these. We saw that we could have transitions. Sorry, you saw that we could have concurrency in transition diagrams, and we can also have these concurrencies in these transition diagrams. Sorry about the mash up the words. What is interesting about these states is that they can be nested. So you can have one state that consists of a bunch of other states. So, for example, a particular, let's say a robot or a computer could be in the state of playing chess. Right? So what is the computer doing? Well, the computer is playing chess. So that is the overall state. Right? But of course, while it is in that state of playing chess, it is actually switching between two smaller states, namely the state when it is moving and the state when the other player is moving. So there are two states, and we are switching between these two states, and this switching between these two states happens while we are in the overall state. So we can nest these state diagrams one inside the other. And the rule is that we can only exit the big state if we have exit the transition diagram that is inside that big state. So the exit of the big state means that all of the smaller nested states are exited. So in Common Catch, these state diagrams are used for modeling communication. For example, between different agents or between the knowledge-based system and the players in an organization. And so you send each other signals. So the users send a signal to the system, or the system sends a signal to the users. And this is most naturally modeled in a state diagram. And using our running example of the housing association, you could model the housing association in a very simplified form as being in two possible states. It is either in the state when it is waiting for the data from the customers and from the houses. So in this state, it is waiting to hear which houses are available and which clients want which houses. So this is the waiting state. And once it has received all the data, then it goes into the assessment state, when it is matching the customers with the houses. Right? And once that is finished, it writes a report and it goes back to the previous state. So this is a very high-level, abstract view of what the housing association does. And of course, we could take each of these high-level states and nest them. Inside them, we could have more detailed states of what's going on while it is doing the assessment.